So welcome to part 2 about redox reactions. So the next part of your notes is determining whether or not a chemical reaction is a redox reaction. So what we're going to do is we're going to identify a couple of ways that you can identify these things called oxidation states. If you remember them, these are the things that we use so that we could balance compounds. So if we take a look at your periodic table, which is in your reference table, these selected oxidation states, are found on the top right-hand corner of the elements box. So you have a couple of choices here. For the most part, whenever you write something, so let's say we have a metal and a non-metal, the first one is going to be positive, and the second item is sometimes, well, most of the time, negative. Okay, so in the case of having carbon first, so let's say we have carbon dioxide, that carbon would have to be either a +2 or a +4. And in the case of oxygen, that's going to be a -2. So we could actually solve this now. So let's do that. We have carbon dioxide. We have a -2. I'm going to multiply that by the subscript, so that's going to be a -4 in total. It must balance out to 0 because this is, I don't see any polyatomic ions. I don't see any brackets. Therefore, the carbon must be a +4 in order for that to be a balanced equation. So let's take a look. So looking at these oxidation states, okay, we need to see, well, there's going to be either a gaining of charge or a reduction of charge, hence the reduction. So one thing to notice if you're trying to figure out if it is in fact a redox reaction, it would not be found in a double replacement reaction. They are not considered redox reaction. But in the case of single replacement reactions, those are. So an example of that would be, say, I don't know, copper solid plus, and I'm making this up, probably doesn't exist, we'll do, I don't know, silver chloride would ultimately swap, so it would be copper chloride now, and the solid would now be silver. So that's what we mean by redox reactions. Now, not all reactions will be spontaneous, so we're also going to, at some point, take a look at a table about activity series. Get back to that another time. So taking a look at these oxidation numbers, like we said, it's listed in the periodic table. Key rule, do not forget, if it is by itself, by definition, it has no charge. So magnesium, a metal, no charge. Looking at our diatomic gases, if they're by themselves, and that's how they're found in nature, it's going to be an oxidation charge of 0. Any metals by themselves, oxidation of 0. So this is where it might get a little bit more complicated. Looking at polyatomic ions. So what we're going to do here is we have to, most of the time, solve for the charge. Okay, the charge of one atom that has multiple oxidation states. So what we do with our polyatomic ions is, just like we were looking at carbon dioxide having to equal 0, in polyatomic ions, they have to equal the charge of the ion. So let's take a look at a good example. We have ammonia. Okay, ammonia is found as an ion. So what we're going to do is, let me give a couple of things. Nitrogen, let's see what our oxidation state is of that. So we have multiple to choose from. So this one is going to be what we need to solve for. Look at all those guys. What we can do is we can narrow it down to the positive numbers. Because like we said, the first one is going to be positive. The second one is going to be negative. So we don't know yet what n is going to be. So we'll just leave that blank. We're going to figure it out. Now hydrogen is found over here. Now we have two choices. Okay. The only logical choice is the negative, because the second species is always going to be negative. So now that we know that hydrogen is a -1, and we're going to multiply that by the subscript. That's what the SOS means. Don't forget to do that. So a -1 times 4 is going to equal -4. Now our sum in total, the charge on that is supposed to be a +1. So work backwards. What plus -4 makes for a +1? So once we do that, we figure out that +5 minus 4 makes for a +1. So we have solved for the oxidation number of a species that had way, way too many. In a compound, like we said, the oxidation states are going to add up and remain 0, showing that they're neutral. So a good example of this would be this. Na has a +1 charge. Chlorine has a -1 charge. There are no brackets because this is a compound. Therefore, +1 minus 1 equals 0, making it a neutral compound. Some other examples that we can look at is what is the oxidation state of chlorine in ionic compounds that are written like this. So let's do that together. We have iron chloride. So the 3 stands for oxidation state. So in this case, it's saying that this is a +3. So we have to figure out, well, what must the oxidation number of chlorine be? Let's go check it out. So we have a couple of choices, right? But because it is the second, it is going to be something we have to choose a negative. So chlorine is a -1. So knowing that, we can figure out this compound has to be multiplied by 3. Therefore, the compound name for iron 3 chloride, our formula would be FeCl3. Now, a little harder to look at would be an oxidation number of chromium in a potassium chromate compound. So what does that mean? Potassium chromate. So let's figure out how we're going to write this. So potassium is a metal. Okay. We'll say that the polyatomic is in orange, so that's going to be chromium for oxygen is the chromate ion, which has a -2 charge. So we know that this has a +1 charge. Therefore, I must have 2 potassiums. So the first thing I did there was I balanced my compound. It's important to do. Once you have a balanced compound, now we have to take a look at all of these different oxidation states. So we know that chromium has potassium has a +1 charge. +1 times 2 is a +2 charge. Now what we're going to do is we're going to break this down a little bit. This 2 is going to have that the first element is going to be positive and the second element is going to be negative. So what does that mean? Looking at just the oxygen, oxygen has a -2 charge. I can look that up on my periodic table, and I'm going to multiply that by 4. When I do that, I have a -8 charge. So what plus -8 is going to make for a -2? And when you do the backwards math, you're going to have a +6. So we can check our math. We have a +6, so +6 minus 8 equals -2. That matches the overall polyatomic ion, so it is correct. So our first step was balancing the equation. Our second step was solving, solving for the oxidation state of the one that had so many. Hope this helps.